we got all the way up until naming coordination compounds, and I handed out last time some practice questions. So if you weren't here last week, then you didn't get those. But I do have them in my office, and I can grab those and give them to you. We'll just do a couple of them now. Naming coordination compounds is intimidating at first, but they kind of follow the same rules that ionic compounds do, because they are, in a real sense, ionic compounds. They're just very, very long names. So a couple rules to remember. You name the ligands based on their fancy names. For a lot of those, that means just kind of changing the ending to O. So like chlorine turns into chloro, sulfate becomes sulfato, and then sulfite becomes sulfido. So you're just changing that last letter to O on a lot of them. Other ones just kind of follow, right? Aqua, meaning water. So those H2O ligands are aqua, and amine ligands are amine, or ammonia ligands are amines. And then when you're writing out the name, or you're writing out the name, the ligands get listed in alphabetical order before the name of the metal cation. So even if you have prefixes on them, you ignore the prefixes. So for something like, I think there's an example down here. All right, so this is diamine tetrachloroplatinate. The amine is going first because of the A in amine, and the chloro comes second because of the C. I mean, this one's not a super great example because di would come before the tetra, but it's because of the first letter of the actual name of the ligand, not the prefix. So after you've gotten those special names for the ligands, and you've sort of listed those out, then you use prefixes to indicate how many of each type of ligand there is. And those are just like the, for most ligands, those are going to be just like molecular compounds. So di, tri, tetra, penta, hexa. We're not going to do any coordination compounds with coordination numbers larger than 6, so hexa is the largest that you'll need. There are special ones for ligands that already have prefixes in them. So ethylene diamine already has di as a part of its whole name. And so we have a few special ones, bis, tris, and tetrakis. And those are going to be, those can only be for certain either, is it why does bidentate sound wrong? Or like blanking on, no, yeah, bidentate and polydentate, just wasn't sounding right to me. And so for bidentate ligands or polydentate ligands, if they have a prefix in the part as a part of their name. And those are then bis, tris, tetrakis, and then, so for this tris ethylene diamine, that's 3 ethylene diamines. And so to separate the tris and indicate like what part of the whole long name is that polydentate ligand, you put it in parentheses. And then finally, after you've named all the ligands and given them all prefixes, then you write the name of the metal. And so for cations, it's just going to be the name of the metal and the charge in parentheses in Roman numerals. If the overall charge of the ligand, like this example here, is negative, or not the overall charge of the ligand, the overall charge of the complex ion is negative, then we still use the charge of the metal ion. That's still the positive charge that that cation has. But because the whole thing is a negative charge, then it's cobaltate. And we change that ending to ATE. So cobalt to cobaltate. So you write the entire name of the complex ion, listing the ligands first, alphabetical order, then the identity of the metal cation. So there's a couple examples here. So platinum, right? So it's a platinum metal cation, but that's last in the name. And we list these in order of in alphabetical order. So that's the diamine comes first, because there's two amine groups. And then the tetrachloro comes next. It's 4 chlorides. And then because the overall charge of the ligand is negative, it's platinate. And this 2 is not that negative charge. It's the charge, the positive charge of that platinum ion. So the reason that this whole complex ion's overall charge is negative is because it has 4 chloride ions, which each have a -1 charge. So -1 charge, or 4 -1 charges is -4. Oops. So -4 from all the chlorides, and then we add the 2 from the platinum, this platinum 2, so the overall charge is -2, or I should say 2 minus. The other example that they gave us, or that we have here, is a cobalt complex ion with a +3 charge. So we list out the hexaamine, which are all of the ligands, and then it's just cobalt 3. So some ligands have charges, other ones are neutral. So there's also this list of more ligands, 2 lists really of ligands. Try and come up with ways of remembering these. Right? For some of them, like cyanide becomes cyano. For the most part, just changing the ending to O. So if you're going in the opposite direction, then the metal comes first, the symbol of the metal. So we're going from name to symbols, or to formula. Then it's all of the neutral molecules, then the ions. And if there's more than one neutral molecule or ion acting as a ligand, list them in alphabetical order based on the chemical symbol. So alphabetical order based on your chemical symbol. Here's a couple examples. So if we're going to name these compounds, how do we start naming this first complex ion? What? Yeah, the ligands. So the ligands are everything that's not the metal ion inside the brackets. Anything outside the brackets is a counter ion to what's on the inside. So our ligands here are going to be the cobalt, or the, not cobalt, carbonyl, and the amine group. So which of those is going to come first? The amine. And we have 5 of those, so it's going to be penta, amine, actually there's 2 M's, pentaamine, monocarbonyl. What's the oxidation state of manganese in this compound? So, yeah, carbonyl's neutral? Carbon monoxide, yeah. Okay, yeah, so it's going to be 2+. So, manganese 2 space sulfate. So it's 2 here because our sulfate has a 2- charge. So then, because all of our ligands are neutral, that means that we have to have a 2 positive charge on the manganese for the overall complex to be neutral. Just stupid long names. It's like longer than anti-disestablishmentarianism. All right, so next one's a little bit easier, a little bit simpler. What are our ligands? What? Chloride is the ligand. Yeah, platinum is here the cation. So we've got 4 chlorine ions, and this is going to be, well, because it's going to be sodium, because we have the sodium out front, and then there's a space. It's going to be tetrachloro. And then what's the overall charge of the complex ion? What? The overall charge of the complex ion. So this part in parentheses, what's the total charge there? -2. 2 minus. Because we have 2 sodiums, that's a 2 plus, so those have to balance. So our complex ion has a negative charge, so we change the ending of platinum to platinate. And then what is the oxidation state of platinum? Yep, 2 plus. Because we have 4 chloro ligands, which are each going to be a 1 minus charge. So everything here, just like in ionic compounds, has to add up to 0. And if you don't have a counter ion present, then it'll add up to whatever the charge of the complex ion is. Right? Everything inside the parentheses, or the brackets. All right, and then structure and isomerization. We're going to go over, well, are there any questions about ligands or naming complex ions, complex compounds? Yeah.
When there's 2 compounds connected together, do you still name them in the order that they go? Like, you have an example here, and it has silver and ammonia together, and it's in one bracket, and then you have another bracket next to it with silver and cyanide.
So there'll be, you would put whichever of those has the positive charge, yeah, you would name first. Just like here, where we have sulfate went second because it has a 2 minus, it has the negative charge. It's the anion in this overall compound. But when we have sodium as the counter ion, then sodium goes first. So your cation is always going to go first. So if you have a positively charged complex ion, that one is named first. And then, so you'll have one really long name, then a space, and then the anion complex ion will go second.
I think I'll just show you.
Yeah, why don't you bring it up here? I don't think I downloaded the examples on my iPad. Yeah, so wait. So it's, we do it like this, Ag and H3, 2, and then Ag, Cn, 2. Yeah, so yeah. So this first one, because the amine ligand is neutrally charged, then the silver is the only charge that's going to matter here. And silver is one of the ions that consistently forms, one of the few transition metals that forms a consistent charge, right? It's always 1 plus. So this will be diamine is it argentum? Because it's I think it's just argentum. Argentum. I don't know if you have to list out the oxidation state because it only has one oxidation state. I'll need to look that one up. So diamine argentum, because that's the positive charge, and then dicyano arginate. Was there a? You don't know. That's right. Yeah. Does that make sense?
So the cyanide or the cyano goes first because that one's the negatively charged one? Why does that one go first? Opposed to the, like, all the other times it was like alphabetical.
So these are two separate complex ions.
Uh-huh.
So you mean like why is the cyano going before
The arginate.
the arginate?
Uh-huh.
Because you always list the ligands before the metal cation. Yeah. Yeah. So the metal cation always goes last. Yeah. Yeah, I don't know if you always put the oxidation state. We'll come back to that. Do you have any other questions about naming these? So yeah, practice is definitely the best thing. So if you didn't get one of those sheets, I'll grab those later and pass those out. You can practice them. And then I also printed out a page that has all of these on it, I think, as well as the rules for naming. So a lot of good practice there. All right, structure and isomerization. Just going to go over this very briefly, like I said, and I'll create a separate video for this. Isomerism is common in coordination compounds because there's all these different places where things can attach, right? And so, especially in something with a coordination number of 6, so it's got 6 separate ligands, especially if those are all monodentate ligands, right? So they're only attaching at one point. That's a lot of different combinations. Now, some of those you're going to be able to, right? Even if you swap two things, you can still like rotate it, and it ends up being the same thing when it's rotated. These isomers are going to be situations where you cannot just rotate it to get something that looks different, right? They'll be actually different, structurally different from each other, no matter which way you orient it. This also has a lot of tie-ins to organic chemistry. So there are two broad categories. One of them is a structural isomer. The other one that's harder to see at first is a stereoisomer. And then there's like a lot of different subcategories. So structural isomers are, there's two different kinds, right? So there's coordination isomers, which occurs when a coordinated ligand exchanges places with an uncoordinated counterion. So between this penta-amino bromo cobalt, right? If we swap the bromine and the chloride, then we have a new compound where it's the chlorine that's coordinated to the cobalt rather than the bromine. So these kinds of exchanges actually will happen all the time unless you're stabilized. And usually they'll occur because everything exists in equilibrium. One of them will be preferred over the other, so you'll have more of it. But unless it's like extremely more preferred, they'll be constantly swapping in and out. Linkage isomers have ligands that can coordinate to the metal in different orientations. These are things like the nitro group, which is a nitrite, that can attach from the nitrogen atom or it can attach from an oxygen atom, and that changes that ligand's name to nitrito or nitrito. Also has some implications for crystal field theory. So linkage isomers, again, this is the best way to see it. So you can see here that this nitro group is attached from the nitrogen, whereas the nitrito group is attached from the oxygen. So they can just kind of take turns coordinating with the metal cation, cobalt in this case. And like I said, that has implications. We're going to talk about this today. But implications for how the d orbitals get impacted by the electronic interactions from that either oxygen or nitrogen. They interact differently, and that causes a different color to be formed from those compounds. Geometric isomers result when ligands bonding to the metal have different spatial arrangements. These are the ones that take just some practice to get down. For something like this, where we have a square planar configuration, pretty easy to see. So this is cis, so they're on the same side. Right, so we've got the chlorines are paired on one side, the nitro groups are paired on the other side, and then in the trans configuration, they're on opposite sides of that metal cation. Not so difficult. Cis means the same side, trans means opposite sides. Like the transatlantic airlines. I think it's an airline, an old airline. One of the first airlines to fly across the Atlantic, crossing the Atlantic, opposite sides. So you can also have cis-trans isomerism in octahedral complexes. And this is harder to see, and you can get other situations where it might look like it's an isomer, but you can actually rotate one of the molecules to match the other one. They're only truly isomers when you can't actually match them. So here we have cis. Again, we've got 4 of these ligands that are the same and 2 that are different. So we can have those 2 next to each other, or we could have 2 on opposite sides. Very convenient when they're colored and they're already arranged. For tetrahedral complexes, you can't actually have a cis-trans isomers, because if you swap any 2, try and draw this. And then, let me see, I need a different color that looks good. So the wedge comes out of the board, the dash goes into the board. All right, if I swap any 2 of these, let me do it like this. All right, if I make, let's make this one black and green. You can just take those and rotate it, and it becomes the other one again. And there's no combination of things that you can swap, because you only have 4 things, and so swapping any 2, just they trade places, and you can still rotate it and get them to be identical. Because one of the things that gets missed in looking at molecules on slides like this, static images, is that the molecules are always moving. And so in any situation, they're going to be in every single possible orientation. So to have something that looks statically different in a solution is not going to be at all different. It'll all average out to be the same thing. This is another type of isomerism. This is a little bit harder to see. But in this case, we have what's called FAC and MER. The FAC isomerism, I always think about as having a face. So you have 3 of the ligands that form faces on either side. So they form triangles, right? So there's a face here of the octahedral, and they represent 3 consecutive points of that. On the MER configuration, there's not any 3 points that form one triangle of the same type of molecule. So they all will form intersecting perpendicular triangles through the metal ligand. So one triangle like this and one triangle like this. In fact, it is short for facials, right? It's making faces. I'll go over this in the video. Part of identifying these, though, is recognizing which configurations are possible based on the number of each type of ligand. So if we have this A3B3, so 3 of each type, then you can have FACMR isomerism. If you don't have that, you can't have that type of isomerism because you'd end up with 2 and 4. If you have 2 and 4, then that's the only type of isomerism you can have in an octahedral complex is cis and trans. Stereoisomers are a special type of isomerism, and it's a really, really cool phenomenon because they're optical isomers. So these types of isomers were first identified when scientists put polarized light. And so polarized light usually comes from a filter. Actually, I think this will work. Sunglasses are often polarized because it helps cut down glare. But on, oh yeah, actually my laptop screen does this. So I can find something that's mostly white. This, of course, won't show up at all in the video, but so if I take this white screen, I take these sunglasses, and I hold it over the screen, and the up-down configuration, you can't see through it. But if I turn it sideways, then you can see through, then there's light passing through the sunglasses. So the light in this case is all oriented in the same direction. A lot of computer screens are that way. There's actually a cool trick where you can remove the polarizer from a computer screen. It's like a thin layer of plastic, especially on cheaper screens like this one. And then you can only see it if you take that polarizer and put it onto glasses or something. So while you're wearing the glasses, you can see what's on the screen. To anybody else, it's just white. So optical isomers will do that in a solution. If you pass light through the liquid, it doesn't do this sort of linear polarization is what this is. It does just not on it with the words today. Circularly polarized. So as the light's passing through the solution, it's getting twisted. And so depending on how much solution it passes through, it twists more. And as it does that, you get actually a prism effect. So if you're looking at it through some other type of linearly polarized glasses, you'll only see certain colors of light. I can share a whole YouTube video that goes into this more. But you get this from optical isomers. So these up here, I think you should be able to see it. Yeah, so these are bidentate ligands. So the thing that makes these different is that there's these, we can like highlight these and make them a little easier to see. All right, so each of these ligands is attached at 2 points, and it is mirrored in this mirror. And so you cannot take this isomer and rotate it in any way to look like the other one. It's similar to your hands, right? Your hands are mirror images of each other. There's no way that you can like rotate them to get them to actually be the same thing if they're in the same plane. And these type of optical or chiral isomers do take some more practice to get down. And so the isomers they're called enantiomers. So there's a right and a left enantiomer. A lot of drugs are like this also. Your body only, I think it's the right-handed isomer of most drugs is the one that's most biologically active. and the other one doesn't do anything because they fit into, so they're chiral molecules that fit into chiral receptors in your body. And so only the one shape will fit. The other one, because it's a unique, different structure, doesn't fit as well or doesn't fit at all. Or I think actually in some cases can be toxic. So these are enantiomers. They have optical activity. So if you have all of one type of isomer, it will rotate the light in one direction. If you have a racemic mixture, oh, that's not in here. Racemic mixture is equal parts of both of them. Then one is rotating the light in one direction, the other one rotates the light in the other direction, and they cancel each other out. You can do this experiment with fructose or glucose. Fructose is better. It's crazy soluble and really cheap. D-glucose. Okay. So those are cool. I will cover those in another video. If you're taking OChem, you should watch that video. You should do the practice problems that'll go with that. And get a model kit, because you'll need one when you take chemistry. Alrighty, now on to valence bond theory. I think I've mentioned this before. I think when I took this part of the class, I had gotten into like a major accident and had like missed a whole week, and so like I don't remember a lot of this from when I took it. Moral of the story, it was a longboarding accident, so make sure you wear a helmet, because I was not wearing a helmet. Spent the weekend in the hospital and another week in bed. So it has actually been really cool to relearn this, and also realize some things that when I took, so I didn't remember any of this, but I took a physical inorganic chemistry class in grad school, graduate level inorganic chemistry class. I hated it. She also graded super hard. Like I got a 50, I think, on the final, and that was a B. So I don't know. Okay, so valence bond theory. This is why, actually if I scroll back up here real fast, for these two, oh wait, no, I missed it, these. So these two nitroisomers, this is going to explain why these are different colors when the nitrogen is bound to the cation center or when the oxygen is bound to the cation center. Because it has an effect on the electrons inside of the cation. So with valence bond theory, we can use that to describe the bonds and types of bonds that form. Remember hybridized orbitals. So we've got some orbital hybridization going on here. And for these bonds between the ligands and the cation, you actually have lone pairs from the ligands lining up with empty orbitals in the complex ion. And so the metal ions are then hybridized according to the geometry of the complex ion. So whether it's tetrahedral, square planar, or octahedral. So we use that valence bond theory for explaining geometry. So why do they form these shapes that they form? But they don't explain properties like color and magnetism, because those fundamentally come from magnetism from the number of paired or unpaired electrons, and the color from the difference in orbital energies. Primarily the energies of the d orbitals in the metal cation. So these complex ions are forming because there's an attraction between the electrons on the ligands and the positive charge on the metal ion. But when those electrons start to get closer to the cation, right, because they're attracted, they also repel the metal electrons in the unhybridized d orbitals. So these internal d orbitals are being affected by the proximity of other electrons. And depending on if the ligands line up with those orbitals or not, we'll see this in the next slide actually, that's going to affect them more or less. So in an octahedral ligand, which is the one that we're going to talk about the most here, we have overlap of 2 d orbitals with ligands. And then because of that overlap, because of that proximity, it increases, like the green one, increases the energies more than the other 3 orbitals, which fall between ligands. Because remember, right, our d orbitals, we've got 1, 2, 3, 4, 5 of them, right? And so we can fill these with different numbers of electrons. So there's 5 total d orbitals. 2 of those are going to be more affected than the others by the proximity of the ligands. And that's because if we can look at the actual crazy shapes of the d orbitals, these are the ions of the ligands, right? There's 6 of them, so this is the octahedral geometry. Here, for these 2 on top, the dx squared minus y squared, which is the one that's on the x-axis and y-axis exactly, lines up exactly with 4 of those ligands. So they're directly pointed at those ligands, very, very close to them. And then the dz squared is on just the z-axis, so it's also very close to the top and bottom ligands in the octahedral complex. So, right, electrons are negatively charged. So if we have negatively charged ligands, which is why they're attracted to the cation in the first place, getting close to the orbitals of the metal cation is going to make it harder for electrons to even exist inside of those orbitals. Because now there's this close negative charge, it's going to make it harder to get in there because the negative charges will repel each other. And so it splits the orbitals. And those 2 orbitals that are aligned with the ligands have higher energy than the other 3 orbitals. And so this is called crystal field splitting. And this is ultimately, if you can logic your way back to how this is affected, that determines everything about whether it's high spin, low spin, all of these other terms. Everything else we're going to talk about is related to the ligands and how much electrical charge they have and their proximity to these d orbitals. So we'll keep coming back to that. All right, so this is called the crystal field splitting energy. And it's the difference between the energy of the d orbitals. Right? So how much these 2 are split, that's what the crystal field splitting energy is. So anything that makes it harder to get into those d orbitals is going to increase the splitting. It's going to take more energy to get into these already sort of negatively charged orbitals. So that magnitude of the splitting is going to depend on a few things. We have strong field complexes and weak field complexes. So strong field complexes, the splitting is large. And we're going to get a list of all of those complexes. It's mostly the nitrogen compounds. And it's going to be, it's going to be the less electronegative ligands. So you take a second to talk about electronegativity, right? So if we have nitrogen, which is going to be less electronegative than something like chlorine, what is that going to do to the electrons around nitrogen compared to the electrons around chlorine? If this is... Yeah. So those electrons are going to be held less tightly by the nitrogen. So that means that they're going to have a wider influence. And so those ligands that have that wider influence, because they're less negatively charged, are going to have their electron clouds closer to the orbitals of the metal cation, closer to those d orbitals. And so those are the strong field complexes, or strong field ligands. And then things like chloride have very high electronegativity. Write this like low En, electronegativity. Chlorine is high. electronegativity, it's going to be holding on to its electrons tightly. And so they're going to have less influence on the d orbitals of the metal cation. Okay. So as I alluded to before, this is what determines the color that different complexes form. The wider that gap is between the two d orbitals that are aligned with the ligands and the 3d orbitals that are not, the higher energy colors you get. So red being a low energy color, purple being the highest, like violet. Because what's happening when these compounds are forming colors is they are absorbing some visible light and exciting electrons up to the higher energy orbitals from the lower energy orbitals. So if I should put this in here. So you got those ones that are down there, these ones that are up here. So depending on this distance, there's an electron that's getting jumped from the low energy orbitals up to the high energy orbitals to absorb light. So other things that are black are absorbing all the wavelengths. Things that are white are reflecting all wavelengths or transmitting if you're seeing through them. Everything else is going to be either absorbing or it's transmitting most of a type of light. For complexes, it's all based on what they're absorbing. So for like a titanium or a hexa aqua titanium 3 complex, it's going to look purple because it's absorbing strongly in the yellow-green region. So you're going to be using this color wheel here. So because it's absorbing all of the complementary colored light to purple, it looks purple because it's removing all of the complementary color, so the other color on the opposite side of the wheel comes out of the color wheel. So then in a spectrophotometer, you can throw this in there and you can scan across all the different wavelengths. And if this is absorbance, you can see that it's absorbing here from really like the 490, really highly from the 490 up to almost 600, so like 580. And so this whole range is this range here that's being absorbed, being removed from all of the light going through the complex. And that amount of light, the wavelengths of those light, we can use to actually calculate how much energy is being absorbed by the compound. And so the energy of a single photon, so the energy of a single photon is, I forgot to look at, I think V is wave number. But expanded, it's h, which is Planck's constant, times the speed of light, divided by the wavelength. So lambda is wavelength. Actually, let me write these down. This is wavelength. This is Planck's constant. This is the speed of light. So by using a spectrophotometer and figuring out what the highest absorbance is, we can calculate the energy that's being absorbed by the photons. The energy that's being absorbed by the photons that causes that color. So because Planck's constant and the speed of light are both constant, this is pretty easy to calculate as long as you can remember what those are. So Planck's constant is 6.626 times 10 to the negative 34 joules seconds. And the speed of light is 3.000 times 10 to the 8 meters per second. So if we have a complex pentaamine mononitro cobalt is yellow, we can estimate that crystal field splitting energy in kilojoules per mole for that ion. So because this is yellow, we're going to need the color wheel to figure out what those what that wavelength is. So it's going to be somewhere between 560 and or sorry, it's going to be the opposite of this 560 to 580. So if the complex is yellow, it's absorbing the complementary color, which is purple. So between 430 and 400, we can just pick an arbitrary number, like 420. So then we just take this equation. The energy of a photon equals Planck's constant times the speed of light divided by the wavelength. So Planck's constant is going to be 6.626 times 10 to the negative 30. That's a weird 3. 34, so it's joule seconds, times 3 times 10 to the 8 meters per second. And then divide that by our wavelength. This is, I mean, you can see here that like this peak is pretty broad, so it's kind of like picking in that area to get a general idea. So this is going to be 420 nanometers. We have to convert it to meters, and we could do that by just tacking on 420 times 10 to the negative 9, and that's going to be meters. So then it's 6.626 e to the negative 34 times 3 e to the 8 divided by 420 e to the negative 9. So that's a very small number, 4.73 times 10 to the negative 19 joules. But we want to get this answer in kilojoules per mole. So this is the energy for the transition of a single electron in this cobalt complex. But if we want it in moles, how do you get from a single atom to moles of an atom? Yes, Avogadro's number. So we'll take this 4.73 times 10 to the negative 19, and that's joules. We can call this joules per atom because it's one electron in one atom of the cobalt complex, or in one complex. Let's just call it complex ion times times 6.022 times 10 to the 23 complex ions, and that's 1 mole of the complex ions. So if you're concerned about getting the correct units, that's how the units work out. 4.73 e to the negative 19 times 6.022 e to the 23. So we're almost there. That's 2.85 times 10 to the 5 joules per mole. So if we just divide by 1,000, it'll be 2.8 or 285 kilojoules per mole. It's actually a lot of energy. But that's getting a lot of ions to all make the exact same transition. So why do you think that, or any guesses as to why this is not so sharp, why it's not just a single wavelength of light? Why is it a whole range? They're all probably making the same jump, but yeah, orientation, the number of them making it at the same time, or if one makes one jump and then that light is then pass through to another one, you get other jumps made. But because it's a whole solution, you have things happening not all at exactly the same time. But you can calculate approximately what the energy of the transition is going to be. You can actually do this kind of thing for a lot of stuff. One of the projects that my brother worked on, so basically everything's vibrating, and then you can find like the frequency of like bond vibrations, and you can use lasers to target that frequency and then slowly turn up the energy until the bond breaks. And then you see a huge change in the spike of or in the readout of your instrument. And so he was measuring the bond dissociation energies of different compounds with lasers, which is just like super cool. All right, so crystal field strength. So this is what's determining, I mean, we could use this to figure out, okay, what is the energy that's being absorbed? But what determines how much energy is absorbed? Like, what does this actually tell us about these compounds? So as the list I alluded to before, or talked about before, we have different types of ligands. And again, those ligands are affecting the d orbitals, and how much they affect the d orbitals, how hard they make it to get into those d orbitals, is what's causing and determining the delta, the crystal field splitting energy. So these are cyanide, nitrite, this is ethylene diamine, or amine groups are typically strong field ligands, while anything with oxygen or any halide ligands are going to have a small crystal field splitting energy, and they're typically weak field. This is again because these are all more electronegative elements than even ethylene diamine. Right? It's got 2 amine groups in it. These have lower electronegativities, so they're holding onto their electrons more loosely, so they have a greater effect on the d orbital electrons and cause greater splitting. And then the metal ion will also have an effect on how much splitting there is, because if you have a higher charged ion, right, if we had like manganese 7 plus, right, that's going to have a much stronger attraction to the electrons on these ligands, which will draw them closer to its own orbitals, which will increase the field splitting, crystal field splitting energy. All right. So that in turn has an effect on the magnetic properties for a specific group of transition metals. Do you remember Hund's rule? That's where you have to fill each orbital with 1 electron first, and then you start doubling them up. So that's super easy when all of the d orbitals have the same amount of energy, because it doesn't matter which one we fill first even. You can go 1 all the way across, and that's fine. When you have these orbitals split into 2 different energy levels, then we now have to make a decision. So let's call this one the large, and then we'll do one where they're closer, so a small. So when we're adding these electrons, or when these electrons get added into these orbitals, we have 2 choices once we've filled in the lower energy orbitals, because lower energy orbitals always fill first. Those options are either pair an electron with another one, in a lower energy orbital, or we can have it jump to a higher energy orbital. And essentially what's going to determine which of those we choose, or which one happens, not even which one we choose, or which one the electron chooses, is that splitting. So if it takes more energy to go to a higher energy orbital than it does to pair with another electron, then it's going to pair with another electron. So in the case of a large crystal field splitting, deleted the wrong one, it will pair before it joins the higher energy orbitals. If we have low crystal field splitting, then it will go to a higher energy orbital because that's less energy than pairing up. So in a compound, in a complex ion, your iron with 6 cyanide groups, cyanide is a strong field ligand, which means it's going to have a strong effect on the orbitals, which means it's going to have a large splitting. And because the energy to go from a low energy orbital to a high energy orbital is really high, they'll all pair up first. These are called low spin complexes. Because all the electrons are paired, their spins cancel out. You've got ups with downs. If we swap those ligands out with water instead, water is a weak field ligand, has a small effect on the d orbitals, so they don't split as much. The electrons will all be unpaired before they're paired. And that's a high spin complex because we have lots of unpaired electrons. And those spins add up. And I can remember paramagnetic and diamagnetic. So in complexes with strong field ligands, they have fewer, so strong field ligands have fewer unpaired electrons relative to the free metal ion, so those are low spin complexes. Complexes with weak field ligands are called high spin complexes and have the same number of unpaired electrons as the free metal ion. I do remember this because I remember having a hard time with strong and weak and high and low spin complexes. But if you can relate everything back to how much are these d orbitals split, then everything sort of logically follows from that. Interesting thing too is this only works for D4, D5, D6, and D7 metals. So depending on their charge and oxidation state, could be a number of these. For the other ones, it actually doesn't matter. It doesn't matter because the number of paired or unpaired electrons won't change based on the field splitting. So if we have fewer, so if we had like a D, if we had a D3, for example. So we've got splitting here. Even if we have a high split, high split, I'm mixing all kinds of things up. Even if we had strong field ligands, so we got a high crystal splitting energy, crystal field energy, we still only have 3 electrons to place, so they're all unpaired. Doesn't matter what those 2 other orbitals are doing. If we have something with more electrons than that, so if we have like a D8, so 8 d electrons, then we still go 1, 2, 3, and whether or not this is a large split or a small split, we still did 1, 2, 3, and we do 4, 5, 6, 7, 8. You're always going to fill it in the same way because the 2 high energy orbitals have the same energy. So there I paired up the bottom ones first. Still the D8, right? So if I go 1, 2, 3, 4, 5, 6, 7, 8, end up with the same thing. Okay, so how many unpaired electrons are there in the complex ion hexachloro iron 3? How many electrons is this iron going to have? One, 2, 3, 4, 5, 6, 7, 8. What's the charge of, what's the oxidation state of the iron? 3. Oh, you meant that's what you meant. Okay, yeah, so the oxidation state on the iron is going to be 3. This is going to be a 3 plus. So we go 1, 2, 3. So it's got 5 electrons. So it's going to be a D5. Is there going to be a large split or a small crystal splitting energy? Crystal field energy? Small. It's going to be small because chloride is a weak field ligand, because chloride is really electronegative, so it's holding onto its electrons tightly, not affecting the d orbitals. So take our 5 electrons and say 1, 2, 3, and then because it's easier to go to a high orbital than it is to pair, 4, 5. So as a D5, we have weak field ligands. Alrighty, how about for cobalt? Hexacyanocobalt. How many electrons do we have on cobalt? Yeah, cobalt's a +2. So cobalt, 7 electrons to place. So it's a D7. And then is cyanide strong or a weak field ligand? Strong. Strong field. So because strong field ligand, then our energy here, or split, is going to be, I guess I wrote this is going to be small, but this one's large. And it's going to be a D7. So we'll go 1, 2, 3. And now it's going to take more energy to go to a high orbital than it is to pair. So we're going to pair first. 3, 4, 5, 6, 7. So one of those electrons does have to go up there, but just one. So it's always just the electrons that are on the metal cation. All right, this looks a little bit different for tetrahedral and square planar complexes because now we've changed where the ligands are. So in a tetrahedral complex, right, if we've got the ion or the ligands all coming from these corners, they're not particularly close to any of the ligands or any of the d orbitals. So like, whatever. All right, so if these are all our d orbitals, these ligands are placed in between all of these. And so it's kind of close to, they're kind of close to the dxy and the dxz and the dyz. So those ones in between the two axes. So it's a little closer to these three, and it's flipped from the octahedral. But because it's not directly aligned with any of those, that split is not very big. So they're typically high spin. So we get lots of unpaired electrons. So regardless of what ligands are attached, that delta is going to be small. For square planar complexes, you get this really weird really weird setup where the x and the y, or the ligands are on the x and the y, so they're directly aligned with the x squared y squared. So x squared y squared is this one. So directly aligned with all of those. So that's going to be greatly affected by those ligands. But then also the dxy is going to be kind of affected by those ligands because it's on the same plane. It's just off by 45 degrees. And so that's why that one comes next. And then dz squared, can't exactly explain that one. I guess in some orientations it might be aligned right? 2 of these might be aligned with the poles there, but going to be less affected than x, y, and x squared, y squared. And then these 2 that are intersecting the vertical plane are going to be pretty much unaffected. But all of it comes down to is the proximity of the ligands to the d orbitals. Oh, and these are always going to be low spin. Because if we start filling these in, we have to fill them in as 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, so they're pretty much always going to be all paired up, or as paired as their metal cation on its own. All right, I know it's 622. These are just some applications of coordination compounds, so we're going to rock through them pretty quick. I think like all the applications are always the most interesting to me, because like, well, what can you do with this stuff? I mentioned this one before. Chelating agents are used to treat heavy metal poisoning, specifically calcium, EDTA, because the complex with lead is more stable than with the calcium in it. So then it's excreted by your body and prevented from interacting in negative ways. Also for chemical analysis, you can use some ligands for selective specific, or some ligands are selective for specific metals and can be used for chemical analysis. Thiocyanate is used to test for cobalt solution, or cobalt makes a blue solution, and in iron it'll make a deep red solution. And then other ligands form colored precipitates. So you can use that to determine if you have iron 3 or cobalt 2. For coloring agents as well, right? All of these complexes have, which is just really interesting and kind of coincidental, that everything else is like white, all the other compounds, and you get these coordination compounds that just have a specific energy difference in their orbitals that causes wavelengths of light that we see, that we can see as colors, really. So iron blue is used in ink, paint, cosmetics, blueprints, and then hexocyano complexes. You can also use them in the human body, right? Well, your human body has ligands. Hemoglobin is one of them. Right? It's a ligand of iron, heme. So body uses it to transport oxygen. Every muscle fiber, I think, has a cobalt in it, because it's using the cobalt to actually, I don't know if you've ever seen like a molecular structure of a muscle fiber. It's like this crazy walking finger thing. It's kind of horrifying. But every time you're moving your arm, like that's what's happening, just really fast. So those are used in there. Yeah, and then so hemoglobin, cytochrome C, both also contains heme, which is a complex of iron and a fat, just connected to the protein. Cytochrome C is what your body uses the last step of the glucose cycle, or the electron transport chain. Right? That's how your cells respirate. And actually, a couple of the fumigants that I've used in my research targeted this enzyme specifically. And this is what makes cyanide so toxic, is it shuts down this cytochrome C, or well, cytochrome C oxidase, so the enzyme that works with it. And then, right, hemoglobin is a biomolecule. Like carbon monoxide binds really well to hemoglobin, which is why that's toxic, because it makes it so your body cannot pick up oxygen. Other biomolecules, such as carbonic anhydrase, catalyze the reaction between water and CO2 as part of respiration. And it's zinc bound in a tetrahedral complex. The 3 sites occupied by nitrogen atoms form surrounding amino acids, and then there's 1 site that binds the water molecule. Last one, chlorophyll. Also porphyrin-based. It's just like crazy cool ring structures, but using magnesium instead of iron. and then no surrounding protein.